So we looked at the distribution of precipitation. One of the main things about precipitation is that humanity depends on it not only for drinking and other uses, but for growing crops and of course all the vegetation on land. So there is the terrestrial biosphere or vegetation. So there are satellites which can measure the radiation at certain wavelengths which correspond to chlorophyll. So if something looks green, then it's absorbing everything other than green. So using these kind of simple ideas and some algorithms that convert the radiation that is being measured by the satellite into amounts of chlorophyll, extent of leaf area, canopy cover, and so on and so forth. So this is just global vegetation distribution, and enhanced vegetation index EVI, which represents the concentration of leaf vegetation. So obviously you can see forests like the Amazonia, the Central African forests, parts of Southeast Asia, Asia and South Asia and Europe, and so on. We talked about the contrasts in rainfall across the US, for example. So the mountains and the vegetation there, the drier regions in the middle, and wetter regions with the warm temperatures, moisture, rainfall, and so on over here. Canada has a nice distribution of boreal forests, temperate and boreal forests, and so on and so forth, right? Similar thing obviously exists on in the ocean as well. Bit more complicated because in the ocean nutrients are supplied often from the colder waters coming up. So there are regions which we mentioned before. We said there is cold water here around Galapagos. We will see that there are colder waters along many coasts. So you can see the eastern side of the oceans have more chlorophyll. Of course, there are also signals mixed in with the rivers. Rivers bring in a lot of organic matter and what are called colored dissolved organic matter from the runoff. So you can see those also here: Congo, Zaire, Amazon River, Orinoco, and here the Ganga, Brahmaputra, Irrawaddy, and so on. And strong upwelling region we will see in the east. We mentioned southwesterly winds create upwelling here. So we will use Coriolis and wind directions to explain where the upwellings occur and how that leads to chlorophyll. But here you can also see that just like the rainfall and sea surface temperatures and surface temperatures were moving back and forth with the sun, you can see that there is similar movements, and there are combinations on land of sunlight being available to create spring blooms and fall disappearance of leaf, and that also appeared in our carbon measurement. Remember the Charles Keeling, David Keeling curve had the sawtooth pattern which relates to disappearance of photosynthesis in the fall-winter months. Of course, that's got hemispherically opposed patterns depending on where spring and summer. The extent of rainfall and ITCZ movement also shows here with vegetation changing. In the ocean, I briefly mentioned that trade winds create water going away from the equator because of rightward push here, leftward push here, and that doesn't move. So you can in fact see that the upwelling gets stronger and weaker with season as trade winds get stronger and weaker. So boreal summer months, the upwelling is strong, chlorophyll is strong, extends more westward. The warm regions remain less productive, and the regions where Hadley cell comes down on land are deserts, and because of the monsoon the deserts go northeastward over here. But in the ocean you have a similar desert in the ocean which corresponds to the subtropical high that we talked about. We will see a little bit more detail that the trade winds and the westerlies together here create a clockwise circulation which leads to convergence of water into the middle. When there is upwelling, cold waters come up and there are nutrients like nitrate in the water that come up, and there is enough light near the surface, then chlorophyll bloom happens. But if waters converge, then waters sink, then there is warm water piled up but there are no nutrients. So those are the deserts of the ocean. So there is no surface production, but there can be light going deeper inside and nutrients below the surface, so you can still have subsurface chlorophyll, what are often known as subsurface chlorophyll maximum, and so on and so forth. So amazing features that you can see. There are spring blooms here and here which are very important, and in the winter cold temperatures, the surface layers get cold and deep and there is no light, but when sun comes up, suddenly the warming creates a thin layer of nutrients with high concentration and light, so you get what are called spring blooms at high latitudes that are related to specific ocean dynamics. So it's fascinating to look at these animations and understand all these features. Of course, you have glacier covered regions which have some color at the edges, but mostly just glaciers, leading to a hydrologic cycle, because evaporation, precipitation obviously are part of the hydrologic cycle. You understand, I think, intuitively what hydrologic cycle means. So here we are looking at energy added and temperature. So if you start with ice at 0 degrees centigrade, then you add the energy needed to melt the ice, so the heat effects of heat added delta H on the temperature of 1 gram of water. Starting from ice at minus 30 degrees centigrade here, we need to add about 63 joules to warm it up to the melting point. So here it is still ice. It was super frozen cold ice here, but adding energy 63 joules brings it to ice at 0 degrees centigrade. Then you add the 333 joules required to melt the ice here from 0 degrees centigrade to 0 degrees centigrade water. So ice to water. So this is a combination of ice and water here as ice keeps melting. Once all ice is melted into water, adding more heat causes the water temperature to increase until you reach the boiling temperature. So we know that water slope of the line here is the heat capacity of the water at constant pressure. So Cp water constant pressure heat capacity of water, delta H over delta T, is 4.2 joules per gram degree centigrade, as we saw before while comparing to the atmosphere. Once the water boils, any added heat is used to vaporize water, and the temperature stays at the boiling point until all water is vaporized. The latent heat of vaporization is about 2270 joules per gram. Thus, the energy required to vaporize water is more than 5 times as much as to warm it from 0 degrees to 100 degrees centigrade. Okay, so we're going here from 0 degrees to boiling point. So we're going here from 396 joules to 815 joules. Okay, so these numbers you have seen before somewhere, I'm sure, but it's just kind of interesting to look at it. And of course, the difference between vaporization and evaporation is that in evaporation we are grabbing molecules of water out of the water, breaking the hydrogen bonds, taking energy out of the water, cooling the water, putting that energy into water vapor in the atmosphere, which is then released when that water condenses. And that's the story of hydrologic cycle. We can look at it in terms of picture of convective cloud, for example. Warming from latent heat released during the condensation makes the interior of cloud more buoyant than the surrounding air, and thus intensifies convection. What does that mean? We have evaporation, rising air, Rising air expands and cools. Condensation releases the heat, makes it more buoyant, and it keeps rising till there is a complete condensation, and either the cloud remains in the cloud form, or based on other processes it might get saturated and start raining, which means to put another molecule of water vapor you have to basically take out a molecule of water, and that process tends to be centered in the cloud. When cloud is spread out like this, the edges are not having this positive feedback of expanding air, condensing, releasing energy, and keep going up. Okay, so that's how you get tall cumulonimbus clouds that we talked about before. The hydrologic processes has some key processes that hydrologic cycle has some key processes that we mentioned: evaporation or evapotranspiration, which is basically evaporation mediated by vegetation. So everybody is evaporating: soil, vegetation, lakes, oceans, and so on, which is condensing, being transported as cloud. Lots of it falls back on the ocean. About 14% out of the 100% of evaporation falls back on the ocean. A lot of it gets carried, 14% gets carried onto land and precipitates over land, creates surface runoff and infiltration and ground flow. The water table goes back to the ocean or into the rivers, and then streams and into the ocean, or becomes part of the soil moisture cycle, and there is the water table. Wherever water table surfaces, you have water bodies like lakes and ponds and so on and so forth. So these also carry nutrients, organic matter, and carbonic acid and calcium ions and so on and so forth, that all runs into the ocean. So this is part of the salt cycle that also maintains salinity in the ocean at nearly constant values for hundreds of millions of years. And of course, now with global warming, the issues are how we are using water and how we are extracting groundwater for irrigation and changing the hydrologic cycle, and also the global warming itself and how that is changing amount of evaporation, condensation, transportation, and so on and so forth. So hydrologic cycle is a big part of the climate cycle. The key question is whether hydrologic cycle is accelerating under global warming, and this debate goes on. So you can look at some numbers. This is already old, 2007, but the approximate numbers remain the same in terms of the amount of water moving around. So you can see here, this is in cubic kilometers per year for exchanges, 1,000 cubic kilometer for storage. So these numbers are in thousands of cubic kilometers, and the fluxes are in 1,000 cubic kilometers per year. Massive amount of water is being moved through the atmosphere. You may have heard expressions like atmospheric river, which bring the so-called Pineapple Express and heavy storms and rains and snow into California, for example. So that's you can think of Amazon as being the biggest river. There are similar rivers in the atmosphere. Okay, so 413,000 cubic kilometer per year here. Ice is holding 26,350 kilometers as water. Ocean precipitation is 373,000 cubic kilometers per year, so the rest is falling here, 113 or so. So ocean to land water transport is 12.5 is 40. Atmosphere is holding, if you integrate all the water vapor, 12.7 thousand cubic kilometers of water. Evaporation on land is 73, much smaller than ocean evaporation. So that includes evapotranspiration as well. So percolation, permafrost storage, groundwater storage, soil moisture, surface flow, rivers and lakes. So you can see the various numbers. So just like we did carbon cycle and the fluxes, we also do hydrologic cycle molecule, and the fluxes and the reservoirs. You can do residence times, but typically water molecule in the atmosphere has a residence time about 4 to 10 days depending on where you are. And we have to also remember that we said water is a feedback greenhouse gas, which means as atmosphere gets warmer, its ability to hold water vapor goes up, which means tropics have more water vapor than the poles. Lower atmosphere has much more water vapor than the upper atmosphere, and with global warming, atmosphere in general is beginning to hold more moisture, as we already said several times. So this is the story of biosphere and the hydrologic cycle. Very brief introduction, but the issue of how these things change under global warming is much more complicated. There are many non-linearities. Remember, water vapor is with Clausius Clapeyron is the most non-linear process in the atmosphere. Okay.